Hello, Algebra 1 students. Congratulations on getting through Topic 7, which was our Introductions to Quadratics and Vertex Form, and welcome to Topic 8. Topic 8 has a pretty impressive sounding title. I'll zoom in on it here. It says Polynomial, and we're going to work on that word, Operations and Factoring. Now, when we talk about operations in math, we know a few operators. Operators are like addition, subtraction, multiplication, division, squares, square roots. Think about the different letters in PEMDAS, and generally each of those is an operator. So when we say polynomial operations, what we're really going to learn is how to add, subtract, multiply, and then divide polynomials. The first three, add, subtracting, and multiplying, are really the first half of this unit, and I think that's the easier half. Then the second half of the unit is where we get into division, and our fancy way for division is to say factoring. That gets a little bit more challenging. So there are two goals in this. Learning goal 22 is performing polynomial operations, just addition, subtraction, and multiplication. Learning goal 23 is going to be the factoring or division part, and they are both essential. You will need these all the time this year, next year in geometry, and especially in algebra 2, and you have to be good at them. I will say one of the biggest deficits my upper level math students, the students in AP calculus and pre-calculus and trigonometry, one of the biggest deficits or holes that they have are that they don't remember how to factor, and a lot of that is because you don't practice it enough, right? Practice improves performance. The more you practice, the better you get. So let's get on to today. Today's lesson should actually be a very mellow one, I hope. We have two daily learning targets for today. We want to understand the definition of a polynomial. What is this weird sounding word that I'm saying? And then we also want to be able to add and subtract polynomials. So to get started, we're just going to see how you do with adding and subtracting polynomials. So we're going to see if you know how to simplify two expressions. Now, when we say simplify in math, usually we mean combine like terms. So there are two problems here, problem 1 and problem 2, and your goal is to see which terms you can combine together. And I'm actually going to help you quickly on this first one. You should notice that there are 5 different terms here, right? There's this x squared, x cubed, 3x squared, and x. And you want to see which ones can you put together. Can you put them all together? I don't know. And really this is just seeing what you know, maybe what you remember, and what you think. And there's no penalty for being wrong. And if you do finish early, please go ahead and try to solve each of those expressions above if possible. And if it's not possible to solve, just a quick sentence, why, would be great. So go ahead now, pause this video, take a few minutes, combine those like terms, work with the people around you, and unpause when you're ready, and we'll see how you did. All right, you're back. Let's go ahead and take a peek at each of these. So when we combine like terms, really there are two parts to every term. The first part is actually invisible for most of these on problem 1. The first part is the coefficient, and a coefficient counts how many of a term are there. The coefficients are always attached by multiplication. You could argue division too, but you can always write division as multiplication. So on problem 1, there is an invisible 1 attached to this x squared, a positive 1 attached to this x cubed, a negative 3 attached to the x squared, a negative 1, and a positive 1. So there are 5 coefficients here, 1, 1, negative 3, negative 1, and 1. And a coefficient counts how many of a term there are, which means everything else after the coefficient is the actual term. And in order to combine terms together, everything else after the coefficient has to be the same. So as we work through today, you're going to find a couple different ways to identify like terms. And the first method I'm going to show you is using shapes. A lot of times I use different colors, but I know you guys don't have the different colors in front of you, so I'm just going to use different shapes to start. With this x squared, I'm just going to use a square because it has a square, but it really doesn't matter. So we have one of these x squareds. Are there any other x squareds that we can combine that with? Well, certainly, there's a negative 3 of those x squareds and a negative 1 of those x squareds. And you might notice here that I actually used that square to trap or to encapsulate the negatives, or if there was a plus, the positives out front. We need to include those signs so we know what to do. Now, to actually combine those terms, take a look, we do what the coefficients tell us. So we have positive one of these, we're taking away 3, and then we're taking away 1 more. And in fact, to make this a little bit more clear, I'm going to do 2 separate things with this. First, I'm actually going to write those like terms right next to each other. So I have 1 of those x squareds minus 3 of them minus 1 of them. This is called the commutative property. It means we're allowed to move the terms anywhere we want as long as we keep the signs with them. The second thing I'm going to do to show you what we're going to do over here is I'm just going to write these separately, 1 minus 3 minus 1, just so we can remember how to do this. Now, although you could do 1 minus 3, which is negative 2, and then bring down the minus 1, and negative 2 minus 1, which is negative 3, I think maybe the faster way to do this, and again, there's nothing wrong with that, I'm just going to show you a faster way over here. If you had 1 minus 3 minus 1 and you rewrote this as 1 minus 1 minus 3, don't the 1 and minus 1s cancel and just leave you with minus 3? We can do that with the terms over here too. We have a 1x squared and a minus 1x squared. Those guys just cancel and just leave us with negative 3 of those x squareds. Either way, you should end up with negative 3 of those. Notice that the exponent didn't change, the x didn't change. The coefficients count how many of these we have. We are not changing those with addition and subtraction. Okay, that took forever, so let's go ahead and look at the other ones here. We also have positive 1 of these x cubes. And then we also have positive 1 of these x's. Now, x cubes are different than x squareds, right? The cube and the square, those are different numbers. And this x doesn't look like it has any exponent. Technically, it has an invisible 1 there, but we usually don't put that. So I'll pick a different shape. I'll do a cloud. Clouds are cute. There we go. So we have 2 other shapes. So how do we combine them? Well, we don't. They don't have any other like terms. So I have 1 of these x cubes. I kept the positive. And we have 1 of these x's. And don't forget, we didn't have the 1's out front. We don't have to write those. So you could put this as negative 3x squared plus x cubed plus x. And that's about it. Now, some students will have gotten this in a different order. They'll say, well, could I put the x cubed first, and then the x, and then the minus 3x squared at the end? Certainly, you can write this in any order as long as the signs are correct. As long as you have a minus 3 or a negative 3 in front of x squared, a positive 1 in front of x cubed, and a positive 1 in front of x, your answer's right. All right, let's try one more. One other thing you might have to do before you combine like terms, but is involved with simplifying, is you might have to get rid of or drop those parentheses. Now, we've learned a way to drop parentheses before. We did this a bunch last semester. The way we learned to drop parentheses was to distribute, right? Distributing drops parentheses. But then you might quickly pause and think, well, wait, didn't Mr. Grant tell us something about killing puppies when you distribute? And that's very good of you to remember because that's going to come up a lot this unit. If there is an exponent attached to these parentheses, like a 2 or a 3 or anything like that, that completely disables distributive property. You are not allowed to distribute the exponent inside, kills puppies, and you are not allowed to distribute a value inside, kills puppies. That exponent up above, think of it as a blocker. It won't let you do anything. However, if there is no exponent written, technically a 1, but we don't need it, you can at least distribute numbers that are out front or at the back. So if I had something like a 4 here, you could distribute, that's fine. If I had a 4 at the end, you could distribute, that's fine. As long as there isn't that exponent blocker, you're good to go. So on problem 2, we can't combine like terms yet because of those parentheses. Always a good idea to drop the parentheses first. So it says 9x minus, let's put in that invisible 1 that we've worked on before, and distribute that negative 1 to everything inside. This gives us 9x, negative 1 times x is negative 1x, negative 1 times positive 2 is negative 2, okay? Plus 3, plus, and I'm going to put the 1 in front of the x squared. All right, let's identify our like terms now. I'll start with the x squared since we've done those before. There's only one of those. And yeah, there's no other x squared. So I think our answer then is going to have that 1x squared. In fact, we don't even need the 1. Technically, it's a positive 1, but if I start our new expression, our answer, with this, we don't need the positive anymore. We don't even need the 1. All right, let's go ahead and take a look at those x's now. Right, x-wise, we have 9x and a minus 1x. 9 of something minus 1 of something is positive 8 of those x's. Notice how the positive 8 became a plus 8. I know it can be kind of tricky deciding what a positive versus a plus is. Spoilers, they're actually the same thing, but in different contexts. And then last but not least, we have this negative 2 or a minus 2 plus 3. And when you're doing this, you can use your calculator. Just do what the signs say. If this comes first, we don't think of it as a minus, we think of it as a negative. And so it's negative 2 plus 3, which is positive 1. We do have to write this plus 1 at the end. We can't just leave it blank because that would mean plus 0. So we do need to put a plus 1 here, and then we're done. Nothing too terrible. Okay, well, this part at the end says now solve each expression up there if possible. Well, hopefully you guys said it's actually not possible to solve, right? We're not going to figure out what x is equal to in this case. And the reason why is because the original problems, I'm going to erase this up here, the original problems don't have an equal sign. And if the original problems don't have an equal sign, we're not solving, right? We can't find what x is equal to because we only do that when we have an equation to start us off. So in fact, I wrote an equal sign over here. I'm going to try my best to not write too many equal signs. In fact, a lot of times I'm just going to write an arrow just so we don't confuse it and we don't try to do things to, quote, both sides, end quote. There aren't both sides. There's only one side that we're simplifying. So this is not possible. There is no equals sign. Okay, whew, that was long-winded. I'm very sorry, but gosh, you guys know I like to talk. So let's get on to the main part of today, which is mostly vocabulary, right? We've actually learned pretty much everything we need for today in terms of the math part. Here we go. A polynomial, right? And I tried to spell that out for you. Polynomial. Accent on the gnome, right? A polynomial expression has only positive, whoops, trying to switch away from our highlighter here, has only positive, I'll zoom in here, whole number. Now, technically positive is already included in whole numbers. Whole numbers are only positives, but I just wanted to reinforce that with you. So it has only positive whole number exponents. So that means we're only going to have exponents of like 1 or 2 or 10 or a million. We aren't going to have exponents of 1/2, so no square roots here. We're not going to have negative exponents, no weird exponential fractions. Okay, just nice exponents. Polynomials, though, are what we're studying this unit, and it's any expression that has only x to some power or y to some power, nothing else there. We classify or we name these polynomials by how many terms they have. So for example, down below, how many terms are in 3x minus 9? Well, hopefully you said 2, because there is a 3x, that's one term, and there's a minus 9, that's a second term. What about x squared y plus 7/2 x minus 1? Well, we have this x squared y, this 7/2 x, and this minus 1. There are 3 terms. Now, some of you might have said, ooh, x squared y, isn't that 4 terms, right? Because there's an x squared and a y. Well, it turns out that terms are actually separated by specific operations. They're separated by operations of addition and subtraction. And what is holding the x squared and the y together? Well, that's multiplication. So that's actually just one term that's right here, this x squared y. Now, a polynomial is actually what we call an umbrella term. It describes lots and lots and lots and lots of different expressions based on the number of terms. For example, you know another umbrella term. You learned in middle school the name polygon. A polygon is not a five-sided shape. We'll get there in a second. A polygon is an umbrella term for different types of shapes. For example, a square is a polygon. A square is a four-sided shape. A pentagon, that's what you're thinking. A pentagon is a type of polygon. A pentagon has 5 sides. A hexagon has 6 sides. An octagon has, stop sign, 8 sides, and so on and so forth. In fact, this prefix poly that we've seen both these times actually means many. So let's go ahead and classify these polynomials below. Each of these examples below are types of polynomials with their specific name. We're going to start with the very fun and exciting polynomial 8. Well, there is only one term here, and so this is known as a monomial. Right? We've seen mono before, right? Mono means one. Okay. All right. You're going to catch on to this pretty quickly. This next polynomial, 3x plus 8, has 2 terms. And guess what? We call that a binomial, right? Think bicycle, 2 wheels. The next one, x to the 4th plus 2x plus 6 has 3 terms. And you tell me, what's this called? Hopefully you all yelled with joy and said trinomial. And you're right. In fact, trinomials are going to be what we study most this unit. And last but not least, we have 1, 2, 3, 4 terms here. And so this one is called, I hope some of you said quadnomial. We actually don't use any names past 3. In fact, 3 and up, sometimes you'll just hear them called polynomials. So you'll hear monomial, binomial, trinomial pretty commonly, or people will just say polynomial. Yeah, not too bad, right? So, due to that commutative property of addition, we talked about that in the opener, which says you can write addition in any order, technically subtraction too if you keep the sign with it. We actually have some confusion regarding how to write a polynomial expression. For example, I've given you 3 polynomials down below. I'm going to highlight them in 3 different colors here. I would like you, well, I'm trying to highlight them in 3 different colors. Maybe my software isn't going to work, but that's all right. We're pretty close here. And our third one, yes, we've done it. What I'd like you to do is work with your group and decide if those 3 polynomials are the same or different, and then give me a reason why. Just a quick little sentence or a little snippet. So go ahead and pause my video here. It should be pretty quick. Chat with your group. Once you're done, maybe hold a thumbs up or let your teacher know, and then we'll discuss. Ready, set, go. All right, so in the past, I've found you guys do a really nice job with this, and you all pretty much decide the 3 polynomials are, and you could say the same, or I'm going to use the fancy math word, are equivalent, right? That means the same or equal. And then you do a great job of explaining why. You say, well, each of them has this 12x cubed term, and notice it's positive in all 3. Even though it says plus in the other 2, that plus is implied. So they all have a 12x cubed. And they all have this minus 15x. And last but not least, they also have this positive 13x to the 5th. And so if they're made up of exactly the same terms, but in a different order, okay, then they are certainly the same. Now, a little bit more vocabulary, and then we'll jump back to this. If a term has a variable, right, a variable is like a letter, like x here, then the number in front of the variable is the, and we talked about this before, is the coefficient. And if you don't know how to spell it, it's 2 words to the right over here. Each coefficient takes or has the sign in front or to the left of it. And as we mentioned earlier, it counts the amount of that variable. If the coefficient is not written, it's an invisible 1. New word coming up here for you. The degree of a polynomial is the largest exponent in the polynomial. So if we're looking at this up here, what is our largest exponent? Is it a 3? Is it a, what exponent's on this negative 15x? Oh, right, that's an invisible 1. Or is it the 5? Well, hopefully you said, oh, the largest exponent is the 5, and you'd be right. That is actually the degree. Now, to make sure everyone has a similar looking answer, we have what's known as a standard form for polynomials. This tells us that we should write a polynomial with the highest degree, so that's a fancy word for exponent, the highest exponent at the beginning, and work our way down to the lowest degree, the lowest exponent at the end. The leading, I'm going to zoom in on this so you can see it, the leading coefficient is the coefficient that's attached to the term with the highest degree, or the largest exponent. Well, now that we have that down, let's go ahead and actually work that same example and see if we can put it into standard form. Okay, so here was one of those that we saw on the previous page, 12x cubed minus 15x plus 13x to the fifth. This is not in standard form right now, and it's not in standard form first because the largest exponent isn't at the beginning, so we definitely need to reorder this. And we do that by writing the largest exponent term first, which is 13x to the fifth. Then, what goes next? Well, you have two choices between 12x cubed and negative 15x. We have to choose the next largest exponent, which is 12x cubed. 12x cubed is a positive, so plus 12x cubed. And then we finish off with the smallest exponent, which is x to the first, which we don't have to write, negative 15x. This is in standard form because our exponents go largest to smallest. You should also note, by the way, that if you had a constant at the end, so for example, if we ended with like a plus 7, technically that has x attached to it, but it has x to the 0th power. And that's because anything to the 0th power, do you guys remember what anything to the 0th power is? Anything to the 0th power is 1. And so really 7 times 1 is just 7. So if you see 7, it has the 0th power, which means 7 would go at the very end. Anytime you have that constant, that number without an x, it goes at the end in standard form. So this polynomial up here is known as a fifth degree, oops, that 5 did not want to work there, a fifth degree, and I'm trying to jump ahead here, fifth degree because 5 is the largest exponent, and then we count the terms, 1, 2, 3. So it's a fifth degree trinomial expression with a leading coefficient. Well, what number is in front of the largest exponent? That's a 13, so a leading coefficient of 13. We're just really building the foundation for our vocabulary right now. In Algebra 2, you're going to build on that. You're going to use the leading coefficient and the degree of the polynomial to get a better understanding of what the polynomial looks like when you graph it. This year, though, we're just getting the vocab down. Now, you should also realize we've seen polynomials before. In fact, all of first semester, we had linear equations, y equals mx plus b, right? We had something, I'll give a quick example, y equals 3x minus 5. Well, these are binomials, they have two terms, and this x has the first power, so they are binomials of degree 1. Then in topic 7, we studied quadratics, and although it's a little tough for now to classify them with a name, maybe I could give you an example like y equals 3x squared minus 5. That's something we know how to graph. And so you could see that maybe these are binomials, but because of that 2, they certainly have a degree of 2. In fact, after this lesson, most of the polynomials we look at are going to have a degree of 2. That square is going to be the largest exponent we see. All right, let's go ahead and try a little bit of practice here. So there are 4 practice problems, and your goal for each of them is to write them in standard form. Then identify the number of terms, the degree, and this stands for leading coefficient, and you can always look back to the example up above. Last but not least, you have to classify it as a name. As a heads up, some of these might not be polynomials. They might try and trick you. And if they're not, give it your best shot for standard form and how to name it, and then we'll go over them in just a bit. So go ahead, give this a shot, please. Take a few minutes, pause the video. Once you're done, unpause, and we'll see how you did. Ready, set, go. All right, let's get back to it. So we'll start with problem 1. Seems to make sense. Standard form, we need to move the largest exponent first and the smallest exponent, the exponent of 0, to the end. It looks to me like there are two terms. 3y cubed is one term, 16 is the other. They're not like terms, but that's okay. The degree of the polynomial, 3. That's the exponent. The leading coefficient, also 3. That's the number out front. And because there are two terms, this is known as a binomial. All right, problem 2. Problem 2, we need to identify the largest exponent first. I'm going to zoom in here. Looks like my largest exponent is the 5th power. Okay, so I'm going to start with negative 4x to the 5th, and then we identify the next largest. I'm going to go ahead and cross this out just so I don't forget what I've done before. This looks like 6x to the 4th. Okay. Next we have 3x cubed minus 7x squared. We'd read this as negative 7, but once it joins the middle of our polynomial expression, we read it as a minus. And then plus 10 to finish everything off. How many terms? 1, 2, 3, 4, 5 terms. What is the degree? Well, that's 5 because it's the largest power. Leading coefficient? Negative 4. And last but not least, there are, since 5 terms, that's beyond what we classify for our polynomials, so we just call it a polynomial. Easy enough. All right, our third one. Well, this one might have thrown you for a loop. Some of you are very clever here, and I love this. You say, well, 5x squared is the largest exponent, and then you realize that actually 3 is the next largest exponent, because technically this is x to the 0th. And then you say, well, 7x to the negative 5th, negative 5 is smaller than 0, so I'm writing it like this. I'm like, cool, super clever. 3, degree of 2, leading coefficient of 5. What do we name this? Well, actually, this is not a polynomial. And it's not a polynomial because we don't have positive exponents here. Right? This needs to be a positive number. Remember that x to the negative 5th is actually 1 over x to the 5th, and that does really weird things to our equations that we don't even study this year. So, it isn't actually a polynomial. Will you get something like this on your test? No, probably not. You might want to know it's not a polynomial, but that's about it. Let's try the last one. All right, standard form. Well, this gets a little bit tricky. We have two different exponents here. One's a number, one's a variable. How do you write that in standard form? Well, hopefully you're already thinking this is probably not a polynomial, and you're right. I don't think there is a standard order for this. I'll put 4 to the x first and then x squared second, the same way. We need to remember, though, that 4 to the x we studied in topic 6. This is known as an exponential when you have x in the power. And that is definitely not a polynomial. There's still two terms. I have no idea what the degree is. You could argue 2, you could say x, and I don't know what the leading coefficient is either. So, again, most of what we're going to deal with will have a maximum exponent of 2. Today we might see a little bit more than that, but it's just good practice. Okay, so the last part of today, the last part of the video at least, is going to be this part 2 here. Because oftentimes, and this is part of our learning target for today, we're going to be given multiple expressions. For example, on 5, we are given a trinomial and another trinomial, and that's supposed to be in green highlighter, but apparently we're not cooperating. There we go. One trinomial and another trinomial, and they are being added together. This is that operations of polynomials. We need to know, at least today, how to add and subtract different polynomials. On 6, we have a binomial subtracting a trinomial, and on 7 and 8, we have different trinomials subtracting from each other. Okay? We are asked to simplify each of these expressions. When an expression is simplified, it traditionally has no parentheses, and all like terms are combined. Remember, from the opener, we can drop the parentheses by distributive, and it's down below if you need help spelling it, property as long as there are no exponents, or rather, they're invisible exponents of 1. So let's go ahead and practice dropping the parentheses on 5. I'll give you one more hint on 6, and then you guys can try 7 and 8. For 5, to drop those parentheses, we need to distribute something. So let's distribute those invisible positive ones that are attached to each. Now, the nice part is when you distribute by multiplying by positive 1, doesn't that just keep numbers the same? 1 times 2 is still 2x cubed. 1 times negative 5x squared. And 1 times x is, I'm going to put the 1 in front, 1x. So if you have these positive 1s, a lot of times we don't even show the distributive property. We just drop the parentheses. I am going to ask you to show this step when you get some practice in on the next page. So I want to see your expression written without any parentheses, like I did here. Okay. Once you're here, though, combining like terms is pretty easy. This is what we've done before, right? Because we are asked to write our expression in standard form, I think it's generally good practice to go through and combine your like terms that have the largest exponents first. So I'm going to start with the cubes here. So we have 2x cubes, and I just quickly looked at all my exponents and saw 3 was the largest. So I'm starting with those. Okay, we have 2 of these x cubes, and we are adding 3 more, or we're adding 1 more. 2 plus 1 will give us 3 of those x cubes. Then I have a negative 5x squared plus 2x squareds. Negative 5 plus 2 gives me negative 3 of those x squareds. I see a positive 1x, and I don't see any other x's, so plus 1x. And last but not least, I see a minus 1, or a minus 1. So I did this one with shapes. The next one I'm going to show you with lines, just so we can keep everything straight. That's as far as we can go. You should also notice that it is written in standard form. I'll rewrite this for clarity here, where we have the largest exponent first of a 3, then a 2, then a 1, then a 0. And that's all we're asking for. Okay, let's try 6, then you guys will try the last 2. If you guys worked ahead, you really want to pay attention to 6 because there's a little trick here. Okay, let's put in those invisible 1s again, just once more. We already know that this 1 out front is a positive 1, so this is just going to stay 4n squared plus 5. But there's something tricky with that second set of parentheses. Do you see it? Well, there's no longer a positive 1 like there was out here on the first problem attached to the parentheses. Now there's a negative 1. And that gets really important because if you distribute a negative 1 to each of the terms on the interior of the parentheses, the numbers don't stay the same. Multiplying by a negative reverses the signs on the inside. Sometimes you hear a negative called an opposite sign. So negative 1 times negative 2n squared will become positive 2n squared. Another way to think of it, a negative times a negative makes a positive. Negative times a positive reverses it, makes it a negative. Negative times negative 4 reverses it and makes it a positive. So don't think you can just drop your parentheses. When the negative is involved, you need to reverse the sign. Again, though, I do need to see this step where you've written everything without the parentheses. And then the second thing we're going to ask you to show just for today is how you identified or what you identified as like terms. Another way you can do it is use some lines. Sometimes I'll see people draw 2 lines under a square. I'm still including that plus sign to show that they're like terms. You have 4 plus 2. That gives you 6n squared. Then we have negative 2n. There's only one of those, so I'm just drawing a single line. So minus 2n. And then what's left? Well, the things that aren't underlined, there's a 5 plus a 4, which makes a positive 9. So that's another way you could show your like terms, because you are going to have to find a way to show those today. You can use colors, you can use a highlighter, lines, shapes, whatever sounds good to you. Okay? So there are 2 problems that remain here. I wish you the best of luck. Please go ahead and try those, and then once you're done, unpause. We'll see how you did, and we'll get you to the last part of today. Ready, set, go. All right, you're back to check your work. I'm excited. Hopefully things went well. We have those invisible 1s here. This first part, though, doesn't matter at all because we have a positive 1 out front. The second part, though, does make a difference. We have a negative 1. It's going to flip those signs. Negative 3x squared plus. There's nothing in front of this x. Let's put that invisible 1. Nothing in front of the minus 8. Let's put a positive 8. Okay, we're looking pretty good here. Now to combine like terms, I'm going to jump back to my old friends, the shapes. We have 4x squareds, and we're taking 3 of those away. That gives us 1 of those x squareds. We have negative 3x's and we're gaining 1. That's negative 2x's. And don't forget, you could always do negative 3 plus 1, negative 3 plus 1 on your calculator to see what those signs are if you're still struggling with those negatives and positives. Last but not least, we have 5 plus 8, which is, of course, positive 13. This is in standard form, largest exponent first. If this was on a multiple choice question on the test, they would almost certainly drop the 1 in front of the x squared. They try to write as little as possible for the answer. Okay. Last but not least, I imagine we're getting the idea here. 5y squared plus 2y minus 4. And I'm just going to distribute the negative that's out front. Technically, there's a 1. I'm just trying to do it with a little less writing. Negative times a negative gives us a positive y squared. I'm going to put the 1. Negative times positive 4 is negative 4. Negative times a negative is a positive. We'll try that underlining game again. We have 5y squareds. We're gaining 1 more. That's going to give us 6y squareds. Then I have positive 2y's. Oops, I guess I went off of my lines here, but that's okay. Minus 4y is going to give me negative 2y. And last but not least, I'm going to circle these so I can see those signs. Negative 4 plus 3 is negative 1. So there you have it. Nothing too terrible at all. The last part of today is really just some practice. There are 13 questions here. And you'll notice that each of the 13 questions either has binomials or trinomials with parentheses. There are 2 things you need to do to get credit here. Well, really 3. First, you need to do this on a separate piece of paper. You can always use the back of this, maybe use your phone to take a picture of the front so that way you don't have to flip back and forth, or you can use a separate piece of paper. Second, you need to write each of these without parentheses first. I do not just want you to go from 1 and just say, oh, it matches this answer over here. I need to see 2 things. First, I need to see this without parentheses. Pretend this is on the back. This would be 7x plus 4 minus 2x minus 9. The negative has to distribute to both. And second, I need you to identify the like terms. Yes, I know it's the worst thing you've had to do today. You'll be fine. Just for today, you need to identify the like terms in any way you want, whether it's with highlighters, shapes, or underlining. So what I mean, this is a 7x, and you do need to grab the sign too, minus 2x. That gives you 5x's. And then it's positive 4 minus 9, which is negative or minus 5. I also avoided using the equal signs. You can use an equal sign if you want. So again, this needs to be done on the back or a separate piece of paper. You need to show it without parentheses and identifying like terms. Once you're done with this, please go ahead and show your teacher, and they'll let you know what you can do for the rest of class if there's any extra time. Also, by the way, you really have to think about what these answers are to laugh at it. It is clever, and I'll give you a hint just by highlighting the word Roman and highlighting in 3 different colors here. A is one color, MERI is another, and CAN is the last. So this is a funny answer, but you really have to think about it. So good luck, rock stars. I'm so excited to have or to watch you be successful in this unit. We're really only doing 2 things. We're adding, subtracting, multiplying for the first half, and then the last half is the dividing. I'm excited to have you back for lesson 8.02, which will be our introduction to multiplying polynomials.